Howdy! So for my last trick, we want to use the same setup that we did last time, only this time we'll discharge the capacitor and then we'll connect this up to the battery here, and we'll see how fast it charges up and how it charges up. Alright, and it's fairly similar, just a little bit different, but fairly similar. Okay, so 3 capacitor connected to a battery through a resistor charges in proportion to its, what do you think the next part is? Remaining capacity. How much storage it has left. Okay, so remember, in the previous example, when we were discharging the capacitor, it was how much it discharged. It discharged in proportion to its current amount of charge. Right, so for each charge that was there, we rolled a die, and if it turned out 1, it would leave. Sounds reasonable, right? If it was a 2, a 3, a 4, a 5, a 6, it stayed. And for every second, let's say, we rolled the die for every one of the charges that was on the capacitor and let it go. In this case, we do the opposite. We say, okay, this capacitor can hold 10 to the 20 electrons. All right, it can hold maybe less than that, maybe only 23 quadrillion electrons. So we look at that and we say, okay, this capacitor has 23 quadrillion seats, all right? And for each one of those seats, every second we roll a die. And if that die turns out 6, we fill the capacitor, or we fill that seat. We add one more electron to the capacitor. And then, right, we do that again for the next iteration, for the next second, but we have fewer seats, right? So after a few seconds, we only have, I don't know, 12 quadrillion seats. So we've halved our work, right? And so we just keep doing that over and over and over again until this charges up. So that means that over time, we eventually get to this Q max, right, where Qm was going to be C times delta V, right? And we started at 0. We're eventually going to get very, very close to that, and we'll have that exponential increase there, all right? So we'll have an exponential increase for Q. So Q is going to be equal to its maximum value times 1 minus, that's not enough room, oh, that's pretty close. I was closer to the edge than I thought, I think. Q is equal to Q naught times 1 minus e to the minus t over that same time constant, RC. All right? So that 1 minus says that eventually we're going to get to, I should call that Qn, so not the initial. This is its maximum. So we start off here at 0 because at t equals 0, when we start charging, this is equal to 1, so that 1 minus 1 is 0. And in a long, long time, right, this goes to 0, so we have Q equals Qn. So we just have this coming up here, this exponential approach to Q over N. Technically, you should never actually charge it completely, but that ignores the fact that you only have so many electrons, right? So eventually you do fill it up. So that's all the charging, that's all it does. So I guess A is it fills to its maximum. And then B, we have to think about that current, right? We thought about the current last time. We have to think about it again. So what's going on with that current? I don't know if that's the gold or the bronze. The current now exponentially decreases. It still decreases the same way it did before. Okay, so I is equal to Qm this time over Rc times e to the minus t over Rc. And so why does it do that? Well, because we're looking at the remaining capacity, right? So as we go on, the remaining capacity reduces, right? And as the remaining capacity reduces, the the voltage difference between here and here reduces as well, because you keep charging up this capacitor, which means the current here reduces, and it keeps reducing until you get to the point where it's fully charged, at which point e to the minus t over Rc is 0, just like this one is, and the current is 0. So here we're just filling up the seats again. So in a way, this is different from water, because water has a constant flow rate when you're filling up the bottle. But here, if we take this thing and we say, okay, we've got 12 little dots. In the first second, we eliminate 4 of them. Then we have 1, 2, 3, 4, 5, 6, 7, 8. So the second, we eliminate 3. Then we have 5 left over, so we eliminate 2. Then we have 3 left over, so we eliminate 1. We have 2 left over, we eliminate 1. We have 1 left over, we don't eliminate anything. We have 1 left over, we still don't eliminate anything. We have 1 left over, maybe we eliminate something, maybe we don't. Let's say we do, and then it's all over. There's no more current flow, right? So that's more or less what's happening when you're charging your capacitor, all right? You're just filling up those seats, but as you fill up the seats, it takes longer to fill up the remaining ones. Well, it doesn't really take longer. It's just a fact of you only have 1 left at some point. And so, your granularity kicks in and sort of mucks things up. We don't have to worry about that. This will be sufficient for everything that we do. All right? Okay, thank you very much. It was nice talking to you. This is the end of circuits, right? Now that we're done with circuits, we'll go on and take the stuff we know about currents and the stuff we know about charges and move them into magnetism. After magnetism, we'll go into electromagnetism, which will be what happens when we have changing electric and magnetic fields rather than the stable electric and magnetic fields that we have now. And finally, we'll go on to optics, which will be what happens when we change those electromagnetic fields really, really quickly. Okay? All right, well, it's very nice talking to you. I will talk to you right after lunch. Bye now.